We now discuss the basics of integration. Then we can solve some problems. So we consider a bounded functions. F is a bounded function on some closed interval a to b. Then the upper Riemann sum U of for particular partition F is defined as sigma mi times delta xi. Here, a partition P is x0, x1, x2, and so on xn. So graphically, let's say we have some function f. Say this is a, and say this is b, and x0 can assume to be a, xn is b. Now we partition this x1, x2, x3, and so on xn. All right, so now this mi is defined to be supremum of f of x x belongs to xi minus 1 to xi. If f is continuous, a supremum is nothing but maximum because it is attained at some point between xi minus 1 to xi. And of course, xi is less than xi plus 1. So yeah, so this is the upper Riemann sum. So basically the upper Riemann sum here will be the area, this area. If we say this is the maximum, and similarly here, this is this area, and this is this area. Similarly, the lower Riemann sum L of P comma F is defined to be sigma mi delta xi. Here, for the same partition, mi is defined to be infimum of f of x. X belongs to xi minus 1 to xi. So this is the dotted one. Is the area. So by definition, we can see that L of p comma f is less than or equal to u of p comma f. So now, if we refine partition P and call as P prime, that means P is contained in P prime. So we add few more points in between this x0 to xn. If you can see, if we add the points in between the area of under those rectangles cannot be increased because we are taking the maximum. So we have if P prime is the refinement of P, we have U of P prime comma F is less than or equal to U of P comma F. And keep further refining the partitions, we can further reduce this thing, and at the same time, what happens to the lower sum? Lower sum keeps increasing. So if we denote infimum, we denote upper integral as a to b of f as infimum of all the partitions p and similarly we denote the lower integral supremum across all the partitions. We say the integral exists if upper and lower partitions are both are equal. So this is a definition of Riemann integral. Typically, we integrate with respect to a non-decreasing function alpha. In that case, the delta xi can be written as delta alpha of xi. This case, we call it as a Riemann-Stieltjes integral. Another useful characterization of integrability is a function f is integrable with respect, Riemann integrable with respect to alpha if there exists, if for every epsilon positive, there exists a partition P such that u of P comma f comma alpha minus L of P comma f comma alpha is less than epsilon. So this has some definitions of Riemann integration, and we can proceed to solve some problems. The first problem is if f maps a comma b to r and g maps a comma b to r, and is g of x as an increasing function of x, and c is a constant state, the following is true or false. So the question here is as integral a to b of x times d of g of x is same as integral a to b f of x times dx. Here, g of x is x plus c. We show that any partition, the upper sum of the left hand side is same as the upper sum of right hand side. So let partition P is xn, and the upper sum of left-hand side is sigma f of x naught times delta, sorry, f of xi, delta of g of x. Now here, delta of g of xi is nothing but g of xi minus g of xi minus 1 times, now this is xi plus c minus xi minus 1 minus c. This is equal to delta xi, which is same as the upper sum for this partition of the right hand side. Hence, we say that the upper sums of both left and right are same, and similar things can be concluded for the lower sum. And hence, the infimum of upper sum and supremum of lower sum of left and right are same, and hence the integral is same. The question is f maps f comma g maps 8b to r, and an integral a to b f of x d g of x exists, then is f bounded. So this is not true in general. We can produce a counter example. So f maps AB to R, G maps AB to R. Question is if integral f dg of x exists, is f bounded. This is not true. Let take a to be 0, b to be 1, and f to be 1 by x. G is equal to x square. So this is 1 over x. dg is 2x. You can see the integral here is 2. But then f at 0 is unbounded. That's a counterexample. State the following as true or false if this function f on a b close a b is Riemann style just integrable with respect to monotonic linear increasing function, then it is also a Riemann integrable. This is true. And the question is, if f maps a to b as a continuous function such that f is greater than 0 and integral a to b f is 0, then f is identically 0 everywhere. So this can be seen. So we are given f to be positive and integral a to b f dx is 0, then f is 0. So assuming f is integrable, we only deal with upper partitions and take the infimum. So consider any partition. Partition of interval a b to b. So x naught to xn, and we get this as some mi times delta alpha delta xi. Now, because f is always negative and these are positive, and infimum over this p is 0. So this implies that this implies that there exists a partition pi p prime such that sigma I mi times delta xi is less than epsilon for any epsilon. Now, because delta xi is non-zero and positive, the only way one can satisfy this is mi has to be zero. And this implies that uh, in every interval, if the supremum is zero, then the function is identically zero in each of the intervals, and hence the entire function is zero. So f maps closed AB to R be a bounded function, then which of the following are true? If f is Riemann integrable on AB, then f is Riemann integrable on CB for all C, but not conversely true. If f is Riemann integrable on all CB, on CB for all C, f is Riemann integrable on AB, but not conversely. If is Riemann integrable on AB, find only if is Riemann integral on AB for all C belongs to path limit doesn't exist. F is Riemann integral, find only if f is Riemann integral on CB and C belongs to A to B. And further, this limit exists and is equal to A is integral A to BF. So the last statement is true. So now we are given two functions f comma g mapping from AB to R and they're integrable and is max of f comma g and min of f comma g is integrable. Is a question. Now we prove a general result if a function if a function is if a function f is integrable, that is f belongs to, say, Riemann integrable with respect to some non-decreasing function alpha. Then let phi be an increasing function. So phi be a continuous function. Function. Then phi composed with f is Riemann integrable. Assume that we follow the proof from the analysis book by Rudin. Let f be bounded between small m, between a and b. Now phi is domain from to R. Now, because phi is continuous on compact sets, phi is uniformly continuous. Now, given that phi is uniformly continuous, we have the following, that we choose delta less than epsilon, just for convenience. For all x comma y belongs to small m to m. Now assume that there is a partition P such that, and because f is integrable, we can assume P comma f comma alpha minus L of P comma f comma alpha is less than delta square. And let mi comma mi be the max of f over the segments xi minus 1 to xi, and min for small mi. Let us denote that for f. And similarly, let's denote m star I comma small m star I for phi. Now divide the numbers 1, 2, so on n, such that they belong to class A if mi minus mi less than delta is class B if mi minus ami greater than or equal to delta. So whenever I belongs to A, so whenever I belongs to A, we show that we have that mi star minus mi star is less than epsilon. This follows from the continuity of the function, uniform continuity of the function. So whenever we have this, so we have this, the above one. So whenever I belongs to this set, we upper bound mi star minus small mi star less than or equal to um, 2k. K is nothing but supremum of phi of t, small m to capital M over t. So from this, we have the following. Um, so delta times sigma I belongs to B, delta alpha I is less than or equal to sigma I belongs to B This implies that sigma delta alpha I belongs to B is less than delta. So finally, can write u of p comma h comma alpha minus al of p comma h comma alpha as sigma I belongs to a m star minus mi star delta alpha I plus sigma I belongs to p mi star minus small mi star times delta alpha I. So this is nothing but epsilon times alpha of p minus alpha of a plus two k delta. By choice of delta to be less than epsilon, this whole thing can be written as some epsilon times some k prime. And since epsilon is arbitrary, we have this, and hence this phi composed with h with f is integrable. So coming back to our original question, so any integrable function composed with continuous function is integrable. Phi composed with an integral function is integrable. So we want to find the integrability of max of f and g. So max of f and g is nothing but f plus g plus mod f minus g over by 2. Min of fg is f plus g minus mod f minus g by 2 is max is min. Now because f and g, f plus g are integrable, and so does f minus g is integrable. Now mod f minus g is integrable because of the previous result, and gain sum of two integrable functions is integrable. That's why max is integrable here. Similarly, the min is integrable. So we have to evaluate the integral cosine of square root of t by square root of t dt 1 to 4. A simple variable substitution of t is equal to x square gives the following. This is nothing but 2 times sine x 2 into sine 2 minus sine 1. This is the answer.